Now that you know how to draw line structures in the simplest manner possible, the line angle structures, let's talk about isomers and acids and bases. So let's first cover isomers before we talk about acids and bases. So isomers will have the same chemical formula, but they're going to have different pattern in their structure of arrangement of groups of atoms and or atoms. So for example here you have butane. You learn about this in chapter 3. Butane has 4 carbons and of course it has 10 hydrogens. This molecule right here is called 2-methylpropane. Again, you'll learn the naming, the nomenclature in chapter 3. This one still has 4 carbons, and if you count, you're gonna have 10 hydrogens. But look, the way they're arranged, the way the elements or the atoms are arranged is different. So they have the same chemical formula, but they're gonna have a different pattern in their structural drawing. Now, if I am to draw the line angle structure for butane, it's just gonna be like that, where this will be carbon 1, this will be carbon 2, this will be carbon 3, and this will be carbon 4. The hydrogens are not shown, but to satisfy 8 electrons around each of these numbered carbons, you can tell that you'll need 4 bonds around each of these. So that's how you'll know there are 2 hydrogens here, 2 here, 3 there, and 3 on carbon 1. For this one, the structure will be like this. Now you see how clearly the pattern is, the structures are different. They have the same chemical formula, but different structural formula. This one is ethanol. Again, the line angle formula will be like this. We show the hydrogens that are not attached to to carbon. And then here, this is dimethyl ether. It's gonna take the bent shape of water. So again, the general formula for these two guys is C2H6. Both of them will have 2 carbons and 6 hydrogens. But now their structures is different. In fact, this is an alcohol and that's an ether. We talked about functional groups. You understand that. Now, there's importance of this isomerism property because it's gonna affect the physical properties of these compounds or molecules, so to speak. So propanol, one propanol, to draw it, showing line angle formula, one propanol should probably be drawn like that with 3 carbons and an OH. The boiling point is 97.4 degrees. But 2-propanol, which is the isomer of 1-propanol, okay, has a boiling point of 82. In fact, you should note that branching decreases boiling point and melting point. I said that before. Branching means you have something popping out of the longest carbon chain. Their general formula, of course, is C3. Both of them will have the same structure, same chemical formula, which is C3 H what? Someone count. H8. Both of them is C3H8, but they have different structural formula. So another examples of structural formulas are what you see here. Do not confuse isomers with different way of drawing in different orientations, because all these guys are the same. Because I see on carbon 1 I have 2 hydrogens and a chlorine, on carbon 1 2 hydrogens and a chlorine, on carbon 1 2 hydrogens and a chlorine. They are the same. Carbon 2 2 hydrogens and a chlorine, carbon 2 2 hydrogens and a chlorine, carbon 2 2 hydrogens and a chlorine. So all these guys are the same. These are not structural isomers. These are just conformational. These are called conformation. Different conformations of the same molecule. Okay, they have different conformation, but it's the same molecule. Where chlorine is on the on horizontal, here it's down. You can have it up, you can have it horizontal. It's just the same thing. Same applies with this. All these are the same. Because I see 2 chlorines on carbon 1. and I see 3 hydrogens on carbon 2. So all these drawings are the same. They are not isomers. So be careful not to confuse the same molecule drawn in different conformation orientations. You see, the boiling point for all these will be the same, 83.5 for all these 3. The boiling point for these 3 will be 57.3, which means the same. They have the same degree of boiling point. So to remind you, whenever you are writing an equation of reaction, an arrow that's going to be between the reactants and products simply means that the reactants react to form the products. Whenever you have 2 half arrows pointing on opposite sides, that's an equilibrium. Reaction can go equally forward and backward. And then this one is for resonance. We talked about resonance before. Okay, different representation of the same structure by moving bonds and lone pairs of electrons around. Why do we use arrows in organic chemistry? Unfortunately, that's the language we speak. Like you'd speak English, Spanish, French. Organic chemistry uses arrows. That's how we can explain where electrons are coming from and where they are ending. A double-headed arrow moves 2 electrons. Single-headed arrow, what I call fish hook. Okay, so this is double-ended. Fish hook will move a single electron, and usually it forms radicals. The rules are simple. The tail of the arrow starts from electrons where they are, and the head of the arrow points to where those electrons will end up. For example, let's say you're given the nail polish remover we call acetone, the ketone. It's a ketone. It falls under the functional group ketones. You know, if I am to show the electrons between the carbon here and the oxygen, I have to show 4 of them because 2 electrons make 1 bond. Of this double bond, one is going to be a sigma bond, the other one is a pi. Remember, I told you sigma is formed by head-head overlap of orbital. Pi bond is formed by side-side overlap. So in that case, the pi bond is weaker than the sigma. So we use a double-ended arrow to move 2 of these electrons towards the oxygen. Remember, there are 2 lone pairs here. We usually just don't show them unless you are asked to draw the Lewis structure or show all electrons. So the arrow is pushed towards the more electronegative element. In your periodic table, the row that contains carbon, nitrogen, oxygen, I think, and fluorine will have CNOF. Might be, I think it's the second row. Electronegativity increases across the periodic table to your right and upwards. So which means oxygen is more electronegative than carbon. What is electronegativity? If you forgot, I told you in an earlier lecture that electronegativity is the affinity of an element for affinity of an atom of an element for electrons. Like that atom really wants to grab electrons. As you go towards the right, fluorine will really want to hold on electrons tighter than carbon, oxygen, or nitrogen because it's farthest to the right of the periodic table. We don't consider the group 8 elements because those don't gain, don't lose. So in this case, I'm emphasizing electronegativity because that's going to guide you to know where the electrons are going. Usually electrons go from a region where they are more to a region where they are needed. So oxygen being more electronegative than the carbon here, than the carbon there, okay, it's going to want to take those electrons. So we push electrons towards the oxygen and not the other way around. So doing so, you are stealing 1 valent electron from this carbon right here. Because remember, carbon has a valency of 4 and it uses those 4, right? Carbon has a valency of 4. So it uses these 4 to bond, but now you're moving 2 electrons. One of the electron belongs to oxygen, the other one belongs to carbon to make up a bond, right? So if you're moving 2 electrons to oxygen, you're denying this carbon 1 electron. So it's now left with 3 electrons. So in that case, this carbon is going to be positive, meaning you need to add back its electron for the carbon to be octet. The oxygen right now is gonna have, so for the case of oxygen, oxygen had okay, so if you are to consider the valency of oxygen will be 1, 2, 3, 4, 5, 6, will be 6. But the moment you move 2 electrons towards the oxygen, it comes with an extra 1 electron. So the valency becomes 7. Okay, so that's why we have a negative charge here. There's 1 more electron. In other words, one can still use the formal charge calculation, where formal charge equals to number of valent electrons in a free atom. For example, carbon, the valency is 4. There's no lone pair on the carbon, so 0. How many bonds? 3, so minus 3. I'm getting plus 1. That's where the plus came from. The oxygen, the formal charge of the oxygen, the valency of oxygen in the periodic table is 6. It's on main group 6. And then if you look carefully, since oxygen had 2 lone pairs and you just broke the bond and gave those 2 electrons to oxygen, so the oxygen will have 6 electrons, okay, on the outside, or 3 lone pairs, and then there's 1 bond to it, so you get -1. So that's where the -1 could come from. You either gonna reason this way or you're gonna do the FC calculations. So that arrow right here shows resonance. Like this structure can give that structure, and this structure you can do the reverse, because now you're pushing towards the carbon because there's less electron density here. Like I said, you push the electrons towards the side where they're needed. If there's a positive sign, the electrons are lacking there. Remember here, oxygen is partially negative, so it will want those electrons in this state. Okay, but okay, so you do the calculations, you can get a formal charge. And if you want to go back, you can neutralize the positive formal charge by donating the electrons back to get this double bond. And that's what's being done here. You just simply move 1 lone pair back. It gives you back the acetone that you started with. Okay, so the reverse process could be possible for this one, of course. So that's an illustration of where an equilibrium arrow can be used and where resonances can be applied. We use arrows to explain that. So now let's switch gears a little bit and talk about acids and bases. Acid-base properties are very important in organic chemistry. You should know this material like there's no choice. You have to know it. So there's Arrhenius acids, Arrhenius bases, Lewis acid, Lewis bases, and there's Bronster Lowry acid and Bronster Lowry bases. So the one we're gonna start with is Bronster Lowry acid. These are just proton donors. The definition of a Bronster Lowry acid, it should be a proton donor. The definition of a Bronster Lowry base, it should be a proton acceptor. As simple as that. And we're going to show examples right now. So consider a generic acid where you have an acidic hydrogen and something that will fall off. We call it a leaving group or conjugate base. So we usually call this conjugate base. So if you lose part of the structure of the acid, for example, as you would in HCl, where Cl will be the A generic species. So when HCl loses its Cl, you get what we call a proton, and then you get a chloride. Okay, so one would want to know how easy it is for this acid to make protons. So to do that, we usually talk about a Ka value. So what is Ka? Ka is acid dissociation constant. The higher the Ka value you have, the stronger the acid. that acid will readily give you the protons. That's what that means if the Ka value is high. But you can get another value, another property we call pKa. pKa just introduces the log value. Remember to use the negative log of Ka. So here, because of the log, turns out that the lower the pKa value, the stronger the acid. So the higher the Ka value, the lower the pKa value, the stronger the acid. Of course, the opposite is true. Okay? The lower the Ka value will mean a bigger pKa value, and that in turn means that the acid is weak. The weaker the acid. Okay? Now let's get back in the equation. So whenever you're talking about dissociation constant, usually you divide the product of the concentrations of your proton and the anion, A minus, A negative. Like, it's just simple. You just divide the concentration of products over the concentration of the reactants. Okay? So these brackets means concentration, and then divide by the original concentration of your acid. In this case, it would have been HCl. So for HCl, I would have said the Ka of HCl is equal to H plus multiplied by Cl minus divided by HCl, concentration of HCl. Okay, so now I want you to be careful. We usually don't just simply use H plus in reactions, because we know that H plus is going to combine with water. As it combines with water, it's going to give you H3O plus, what we call hydronium. Please note these terms, hydronium, because I'll be using them a lot. Okay, so you get the hydronium ion, the H3O plus. All right, so I've said a larger Ka implies stronger acid. The larger the Ka, the lower the pKa, the stronger the acid. Again, a greater dissociation constant implies this acid readily gives protons when put in water. So what factors will make an acid to be strong? Those factors will stabilize the conjugate base. The conjugate base will be stabilized. Okay, remember the A minus is what falls off after the generic acid has dissociated. So for example, this is a conjugate base. So factors that stabilize the conjugate base. The more stable the conjugate base you have, the quicker you're going to make protons, the stronger the parent acid. I repeat, the more stabilized the conjugate base you have, the quicker the acid will form the protons, or the hydronium, so to speak, and that means you had a strong acid in the first place. Okay, so there are factors that make the conjugate base stable. These factors are very important because that's what will in turn make the acid stronger, the parent acid stronger. So the first factor is electronegativity. An example is this. Now, if you again go back to your periodic table, the second row of your periodic table, carbon, nitrogen, oxygen, and fluorine are on the second period of the periodic table, and the electronegativity again increases across the periodic table. Remember, electronegativity is the affinity of an atom of an element to grab electrons. So we can say that if your conjugate base here, the anion, if it's highly electronegative, then it's going to be more stable, meaning it holds on the electrons better. Those electrons will not be used again to attack something else. So the whole conjugate base becomes stable or stabilized. So electronegativity plays a role. So for example, you see these, if you consider this list of acids, like you have HF, water, ammonia, and CH4. So I would draw the Lewis structures, and basically you're looking at the protons. Can these protons be easily removed to make H plus as per our generic equation? So we have ammonia and then we have water. And then of course we have HF. I'm listing them in order of how they are arranged on the periodic table. So obviously, if this proton is lost, then you're gonna get F minus. If this proton is lost, you get OHO minus and H plus. If one of these is taken out or the molecule dissociates to give you protons, you get H plus and NH2 minus. If one of these dissociates, you're gonna get H plus, assuming these are acids, that so to speak, you get H plus and CH3 minus. So the point I want to make is this: whenever you are deciding which is the conjugate base, which of course is what's left off with negative charges, you can consider electronegativity, because now I have this as my generic, as my anion. Remember we said if you have Ha, you get A minus and H plus. So I'm focusing on the A minus, which is what I'm trying to circle. You have NH2 minus, you have HO minus, and you have F minus. So you realize you have a carbon bonded to hydrogens, nitrogen bonded to hydrogens, oxygen bonded to hydrogen, and F. Out of all these, the one that holds on to these lone pairs is tightest is the fluorine, because it's the most electronegative according to our periodic table. So HF, if this is the most stabilized conjugate base, or A minus, then it means its parent acid HF is the most strongest, followed by H2O, followed by ammonia, followed by CH4. And in fact, this one is very electronegative, so that's why its HF will be way acidic than water, ammonia, or CH4. In fact, if water was acidic, then we'll all be dead because we drink it all the time. So electronegativity stabilizes the conjugate anion, in this case F minus. So the more electronegative the anionic atom in the conjugate base, the better it accepts the negative charge, or the better it holds on the electrons, and the stronger the parent acid, in this case HF. Next is size. Do not confuse. I told you electronegativity increases across and upwards. So if you are to use the first point, then HF still wins as a stronger acid based on electronegativity. But whenever you are going down the periodic table, so for example, where fluorine is, you'll have fluorine, chlorine, bromine, and iodide. Look at your periodic table, main group 7 or 7A, main group 7 on your periodic table. You will see F, chlorine, bromine, and iodide. Those are halogens. So like I said, if you are to consider electronegativity, then F will be forming anions, F minus from HF, okay, which will be taken to be more stable. But that's false. Whenever you're going down the columns of the periodic table, consider size, not electronegativity. So the reason is this. Iodide is way big. It has so many energy shells, so it's big. So there's room to hide the negative electron charge within the anion, within the conjugate base. Hi will give you I minus, HBr will give you Br minus, HCl will give you Cl minus, HF will give you F minus. Of course, all these will be formed alongside their protons. H plus plus that, you have H plus that, and then of course you have F minus plus H plus, whichever order you want to write them. The point is you're making anions. So iodide is the biggest, so there's more volume for the electrons to reside within the anion. So size allows for greater charge stability, which means lower charge density, which means the anion formed or the conjugate formed A minus, for example, if we were to use that as a generic conjugate base, will be very, very stable. So the other one to consider, of course, is gonna be resonance. So I think there's a problem here. We needed to put a C in between. Okay, so next one is resonance. Resonance helps to spread these electrons around on the anion. Okay, so let's say your acid, generic acid, gives you A minus, and A minus can do resonances, then that's going to stabilize it. So for example, if you have the rest of the structure and then you have a carbonate, okay, like that, this structure is what this is right here, versus this one, which will simply be just a carbon structure without resonance. How do I know we can do resonance? Each time you have lone pairs next to a double bond, you can do resonance. For example, I have a lone pair here, I can make a bond here, and this will open up. You need a pi bond for that to open up. You need a pi bond for the double bond to open up. Here there's no double bond next door, so this structure has no resonance. So what does that mean? It means these electrons are available to be used up, but these ones are not available because they keep going back and forth. Because once you draw the resonance structure of that structure in blue, this is the structure you'll end up with. So the oxygen up here will have 3 lone pairs and a negative charge, and then now your double bond is down here with 2 lone pairs. You started with 3, you made a pi bond using one of the lone pairs, you end up with this. So this is resonance stabilization. So if I'm asked to pick one, if I'm asked between this structure and this one, which one is most acidic, I'll definitely pick up this, because I know once this hydrogen is taken out, I'm gonna get this structure in blue, where the H plus will be gone, and then you're left with this conjugate anion. In other words, for when this carboxylic acid dissociates, then you're gonna get carboxylate, and of course you're gonna get H plus. This is the system we are discussing. It's resonance stabilized. Here is whenever you have a parent molecule like this, which is an alcohol. If this has to dissociate at all, you're gonna get what we call an alkoxide, and you're going to get a H plus. So there's no resonance stabilization here. So in other words, this parent acid is stronger than this alcohol, because this parent acid forms a conjugate anion, A minus, which is resonance stabilized. So the other reason is inductive effect, which goes with the presence of electronegative groups that pull electrons inwards towards the structure, and of course hybridization. An sp hybridized element is gonna give you higher acidity than sp2 than sp3 whenever considering CH bonds. All right, so let's give examples here. So what if you react water and HCl? So I know that because oxygen is because chlorine is more electronegative, dipole moments will point towards chlorine, and this will be partially negative, this will be partially positive. These hydrogens are not as acidic as this one right here. So now I know this is the most acidic hydrogen out of these two structures. So this whole molecule will play the role of an acid, and this will play the role of a base. Bases usually use their pi bonds or lone pairs to accept hydrogens, and we're going to do the first mechanism ever for this class using arrows. So The way to do it, you use a lone pair, start from there, and then end up on the positive center, because electrons are negatively charged. The hydrogen here is partially positive due to dipole moments. So opposite charges attract. So this is like a hand going to grab that hydrogen. Then this bond has to break towards the chlorine. So remember, the chlorine right now here has 3 lone pairs. After the bond breaks and donates the 2 electrons that made the bond to chlorine, you're gonna end up with 4 lone pairs. Chlorine has a valency of 7. Now you have 8. That's why you have a negative formal charge. If you do the math after doing this reaction, you're gonna have a lone pair here. If you do the math for the formal charge of oxygen, you're gonna get a positive. Okay. Again, out of these hydrogens, which one is most acidic? I would say this is the most acidic, because once I lose it, I'm gonna get a conjugate anion which is resonance stabilized. So this will play the role of the acid. That's how you know which is the acid, which is the base. And this will play the role of the Bronster Lowry base, which means this will be the proton acceptor. It's accepting. And then this will be the proton donor. It loses that hydrogen. Of course, you no longer see the hydrogen here. You're gonna be left with 3 lone pairs. Here you only have 2 to make an octet on oxygen. Once the oxygen of water accepts the hydrogen, you're gonna be left with 1 lone pair, and of course you do the math, this will be positive. Now, like I said, this structure right here can be resonance stabilized to this. So let's show how it's gonna resonate. So you use your lone pair again, start from the lone pair, that's where the electrons are, and then end up where the electrons are ending up. And then, like, because you have a pi bond, it always have to give way. Okay, so now you're gonna end up with 3 lone pairs, and you're gonna end up with 2 lone pairs here. And then these two electrons made this second bond. This arrow is resonance. So this one is resonance stabilized. So the conjugate anion here is resonance stabilized, which makes this an acid. And the conjugate base here is stabilized by electronegativity, which makes HCl a strong acid. Between this conjugate base A- and this A-, which one is the most stable? Obviously, it's the chlorine, because chlorine is more electronegative than oxygen. So and that's why HCl is a stronger acid than acetic acid, or what we call ethanoic acid. Okay, so examples. So the other factor we mentioned in a previous slide is inductive effect, right? So for inductive effect, it's pool of electronegative elements. This one does not have an electronegative element. All you have here is does not have a strong electronegative element like chlorine. All you have here is hydrogens, but this one has at least a chlorine. So you can imagine that if this loses the acidic proton, you get that conjugate base, anion. If this one loses the acidic hydrogen, you get this conjugate base from the parent acid. So the question is, which of these 2 conjugate bases is more stabilized? The answer is simple. Even though you have resonance in both, you can notice that this one has an electronegative element, which means the electron cloud here, or the electron density, will be reduced, because it's gonna be sucked in towards the more electronegative chlorine. Here all you have is just a hydrogen. Hydrogens are not electronegative. So this one is stabilized further by electronegativity on top of resonance. Both of them have resonances. So that's what makes this molecule stronger acid than this. Evidence is pKa. The lower the pKa, the stronger the acid. Okay, so the electron density is pulled towards the Cl. The closer the Cl is to the oxygen bearing the negative charge, the better it stabilizes the conjugate anion. For example, if you lose this acidic hydrogen from a reaction, from an acid-base reaction, you're going to end up with that, that one for that. This one, once the acidic hydrogen is gone, you're gonna get that. And for this one, once the acidic hydrogen is gone, you're gonna get that. So these are the conjugate anions of these molecules. Remember the principle we are going by: the more stable the conjugate anion is, the stronger the parent acid. Okay, so assume these protons are gone. That's, you're gonna get these structures in red. So you see, based on inductive effect, this chlorine is closest to where the electrons are more, so it has a higher effect of pulling the electron density towards itself. So the closer the electronegative element is to the site where you have high electron density, the higher the inductive effect, the more stable the conjugate, the more stable the conjugate base, the more stable the stronger the acid, the stronger the parent acid. That's what I wanted to say. So I repeat, the closer the electronegative element is to the site where you have great electron density on the conjugate anion, the greater its effect, the greater its inductive effect in stabilizing the conjugate anion, which means the parent acid will be the strongest. So here you can see which of these has the highest pKa. Let's see. The one that has the highest pKa, we can't talk about pKa or given Ka. So which one of these has the largest Ka? Because the larger the Ka, the stronger the acid. The lower the pKa, the stronger the acid. This is the largest Ka value, which means this is the strongest acid of these four molecules. Okay, based on the Ka value given. I might not give you those numbers. You just have to look at the structure and decide which one is more stabilized, which one will give you the most stable conjugate anion, A minus. But here, because you're given the Ka values, that's just added information as evidence to tell you that this is the strongest acid of all, because the chlorine is the closest to the region where you would have high electron density after loss of the proton, after loss of the acidic proton. This one does not have any electronegative element on the structure, so it's the least stabilized. Hybridization. Remember, for alkynes, this has two electron domains, so it's sp hybridized. The Ka value here is the largest, so which means alkyne will be the strongest acid. The pKa is the smallest, which means again the alkyne is the strongest acid of these hydrocarbons, followed by this one, which is sp2. Now let me draw the Lewis so you can know why it's sp2. We talked about this in the last class. You have three electron domains, a double bond, a single bond, and a single bond. So that's sp2 hybridized. Okay, and then this one has the 3 bonds to the hydrogens and this bond right here. So you have 4 electron domains. So this has to be 1s and 3p's. So based on the pKa, the lower the pKa, the stronger the acid. Of course, the alkynes are stronger acids than alkenes, and it happens that alkenes are right in the middle. I already told you that alkenes have double bonds, alkynes have triple bonds, alkenes have all single bonds. So those are factors that tend to stabilize or tend to be used to explain why one molecule is more acidic than the other. Okay, you have a list of acids here with their pKa. So based on pKa, you can decide which one is the strongest acid. Sulfuric acid has -11, so it tends to be the strongest out of this. And of course, alkenes will be the weakest because they have the highest pKa. So we've talked about stabilization of the conjugate base, which makes we've talked about stabilization of conjugate base, which makes stronger acids. Okay, so we talked about electronegativity, and in this case, if we focus on bases, when you use electronegativity within the same row of the periodic table, the more electronegative the atom, the weaker the base it will be. For example, F minus is going to be a weak base when compared to N minus, O minus, or C minus. So this is the weakest base because it holds tightly on electrons, which means it does not want to use them. And then with size, iodide is going to be the weakest base, for example, in halogens, because it's the biggest. Those electrons hide within the structure. A base is characterized by the presence of electrons. Resonance. If you have such a structure, these electrons are rarely available. They keep going back and forth. So this makes this a weaker base compared to a structure like that where there's no resonance. So this is a stronger base than that. Okay. So again, if you are to consider the strength of bases, first, the ones that are negatively charged will be considered to be stronger bases than the ones that are neutral. And then amongst those that are negative, you consider electronegativity. Oxygen is more electronegative than nitrogen, right? So it holds the electrons tight on it. Even though these oxygens have 6 electrons and the nitrogen only has 4, oxygen is mean. So it's a weaker base compared to nitrogen, which we readily want to use the lone pair. So you're using electronegativity at the same time you're using charge. Negatively charged species tend to be more basic than neutral species. Okay. Now in terms of bases, the higher the pKa, the stronger the base. The higher the pKa, the stronger the base. The lower the Ka, the stronger the base. Okay. High pKa, low Ka means stronger base.